So in this video we're looking at two things. First thing we're looking at is geometric series and sort of an introduction to the idea behind a series, and then we're going to see how that relates to annuities. So the question that we start off with is, what happens if we take a set of numbers and the set of numbers has a given pattern, we want to add them all together. Okay, so first off we have our notation to represent our set. Our set, again, it has a pattern, so we have A1 will be the first term, A2 is the second term, A3, A4, and so on. It is just going to be a finite set, which means that it does end at some point. So here, the last term in our set would be, let's say, A sub n. And this would be our set of numbers. We could rewrite this a little bit if we wanted to. We could say, okay, I know what the pattern of this set of numbers is. It's defined by an. And actually, let's sort of change that. Let's say it's defined by a sub I, and I want to do this from I equals 1 to n. So when you look at this value I is going to be our counter. We're going to start off here with I equal to 1, and we're going to go all the way until the last term when I is going to be equal to n, and that'll be when we stop our set of numbers. So that's the basic idea, and then what we want to do with that set of numbers is we want to know what it looks like and what happens if we were to add them up. So I would like to add up all of the terms defined by a sub I. I want to start off with I equal to 1, and I want to go until I get to I equal to n, and that will be the last term that I add up. So this will be just A1 plus A2 plus A3, and I keep going with this all the way until the very last term. The very last term would be a sub n, and we want to know what is this summation going to give us. Okay, so let's just sort of look here at a quick example. If I started off with a sum from 1 to 5, and the terms that I'm adding up are 1 divided by 2 to the power of I. Alright, so here I have my counter starts off at 1, so the very first term that I'm adding up would be I equal to 1, and that first term would be just 1 over 2 to the power of 1 would be 1/2. Then I have my second term. What happens if my counter is equal to 2? So I have 1 over 2 squared, that's going to be 1 over 4. Then my counter is 3. I have 1 over 2 to the power of 3 is going to be 1 over 8. We have 1 over 2 to the power of 4. That's going to be 1 over 16. And then the very last term corresponding to I equal to 5 will be 1 divided by 32. And we want to know what happens if I take all of these 5 numbers and I add them up. Well, in this case, you can get out your calculator and you can do a little bit of work. You end up getting that the sum is going to be 31 over 32. Okay, and that works relatively well if you're only adding up, in this case, 5 terms. But what if we wanted to add up 10 terms, 20 terms, 30 terms? What if we wanted to add up 100 terms? We don't want to have to physically get out a calculator and add up all of these terms. So what we're going to do is try to find out if there is a pattern to what is happening, and then we can use that pattern to determine the sum of any number of terms. Okay? So here we have our sum of 5 numbers giving us 31 over 32, but we wanted to know, is there a pattern that we could sort of extend? So here, if I were to look at just adding up the first term, and this is kind of silly, but here I would just have the sum starting at 1, ending at 1, and I'm just adding up 1 over 2 to the power of I. So if I add up just the first term, I get 1/2. Okay, and there's not really much going on there, but that's how it would work. What if I were to add up the first 2 terms? That's going to be here the sum starting at 1 and going until 2 of 1 over 2 to the power of I, which would be 1/2 plus 1 over 4. And if I add 1/2 and 1 over 4, I'm going to end up with 3 over 4. So let's do this one more time. We have n equal to 3. If I add up the first 3 terms, I have 1 over 2 to the I. That's going to give us 1/2 plus 1 over 4 plus 1 over 8. And putting these three terms together, we're going to end up with 7 divided by 8. So just one last time, let's see what happens if we add up the first 4 terms. So from 1 to 4, we have 1/2 plus 1 over 4 plus 1 over 8 plus 1 over 16. And again, putting all of these together, we're going to end up with 15 divided by 16. So now what we're doing is looking at these terms: 1/2, 3/4, 7/8, 15/16, and we want to know, is there a pattern here developing from one to the next one that we could use to figure out what's going to happen if we were to add up, for example, the first 100 terms. What if we wanted to go from I equals 1 to I equal to 100? Okay, so what's going to be our pattern? Well, let's try to figure this out on the side. We know the sum from 1 to n in general. What is the pattern defined in terms of n for our denominator and for our numerator separate from each other? So first off, let's look at these denominators. Okay, so I have my denominator is 2, 4, 8, 16, and those you have to recognize are just the powers of 2. Okay, here we have 2 to the power of 1, we have 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. So actually what we end up with for the nth term, okay, we end up with 2 to the power of n. So here what we're going to have is 2 to the power of n as our denominator. So for example, if I add up the first 4 terms, my denominator will be 2 to the power of 4. It's going to be 16. Okay, so now how do I figure out what the numerator is? Well, you could go through sort of a more complicated process, but one way of doing it is just noticing that the numerator is specifically equal to the denominator minus 1. It's always 1 less than the denominator. So here, what we have in the numerator will just be 2 to the power of n minus 1. And this is a very nice formula that we could use if we want to figure out what the sum of 5 terms would be, what the sum of 10 terms would be, what the sum of 100 terms would be, and so on. So here, if I look at it, we could say the sum of the first, let's say, 10 terms, 1 over 2 to the power of I. I don't need to write any of this down. I know my denominator will be 2 to the 10, and my numerator will be 2 to the 10 minus 1. So plug that into your calculator, you get just 1024 as your denominator and 1023 as your numerator. And that right there, that would be the sum of adding up 10 of these different terms together. Okay, and that's much faster than actually doing the sum all 10 terms together. And so here, we're going to focus a little bit more on this sort of pattern. Okay, there's a very specific reason why the pattern is so nice for this sum, and that's specifically because this series is actually a geometric series. It's a special type of series which we're going to look at in a moment. So let's go and define what a geometric series is specifically. So a geometric series is a series, so we're adding up the terms, in which every term is obtained by multiplying the previous term by a specific number r. Okay, so what that means is if I'm starting off my series and the first term is going to be, let's say, 4, and the second term is 12. Okay, so how did I get there? Well, going from the first term to the second term, I clearly just multiplied by 3. Okay, so I'm going to be getting each term by multiplying the previous term by a value r, and in this case I'm multiplying it by the value of 3. So now I'm going to take 12, I'm going to again multiply it by 3, and that means that the third term I'm adding up is 36, and I'm going to do that again. I'm going to multiply 36 by 3, and so the next term will be just 108, and I could keep doing this, as many times as I want, and this is going to be defining a geometric series. Okay, so every time I go from one term to the next, I multiply by 3. And so actually, there's a very specific name for that ratio. Okay, if I look at the ratio between any two terms, that common ratio is r. Okay, so here we have r is the common ratio. And for this example, we have that r is equal to just positive 3. And if I want to write this as a summation, there's a general format for a geometric series. So our counter is going to start off at 1. And in this case, we have 1, 2, 3, 4, 5 terms. So our counter is going to end at 5. And then what are the terms that are being added up? Well, we have our first term. The first term is 4. And then we would like to, every time our counter increases by 1, we would like to multiply by the common ratio, and the common ratio is 3. Okay, so here it's going to be 3 to the power of I minus 1. Now it specifically has to be here I minus 1 because that value I, when it starts off at 1, we want this exponent to be 0 because 3 to the 0 is 1. And that means that the first term right here is not going to have the 3 in it. It will just be the 4. Okay, so this right here, this is the standard way that we're going to be writing a geometric series. And we have our common ratio. That's this right here. That's our value of r. And we also have a name for this first term. Okay, this is going to be a. And that is the first term in our geometric series. So in general, what does it look like when you have a geometric series? Well, you have your first term is a, and then you're going to multiply it by r, so you get a times r, and you multiply it by r again, and you get a times r squared, and you keep doing this. You're just multiplying by that common ratio every time, so the power of r just keeps increasing by 1 when you go from one term to the next. So you keep adding all of this up. Okay, and we get to here the very last term, but the very last term will be a times r, and we want to know what's going to be that exponent. Okay, well the exponent there is going to be n minus 1, because we know here we set it up where that exponent was I minus 1, and this is going to be your geometric series. You are starting at I, you are ending at n, and what are the terms being added up? Well, you have a, that's your first term a, and you have your common ratio r, okay, which is what you use to get from one term to the next every time we multiply here by r, and the exponent of r is going to be I minus 1. Okay, so that's the standard form there that we're going to use for a geometric series. Again, we have r is the common ratio, a is the very first term, and one restriction that we do have on a here is that a is going to be non-zero, because if a is 0, well, every term has a in it, so that just means our entire series would just be 0. Okay, so here let's sort of look again at the first example that we saw. It was a geometric series, so if I go back to 1 over 2 to the power of I, starting at 1 and going to 4, the very first term here was 1/2. The second term was 1 over 4, and then we have 1 over 8 and 1 over 16. So you can tell that this right here, that is our a value. A is equal to 1/2. And how do you get from one term to the next? Well, each time all that I'm going to do is multiply by the common ratio, and in this case the common ratio is also 1/2. Okay, so that's our basic sort of idea behind a geometric series. What we're going to do in the next part is just look at one more example and sort of work with the sum of a more complicated geometric series. So here we have a geometric series. It's a little bit more going on to it, and we want to know what the sum is. So we're adding up 6 terms. We have our a is going to be 10. Okay, and we have our common ratio is 5 divided by 4. That's our r value. Now here we don't necessarily need that. We can write out here the first 6 terms relatively quickly, but here I know my first term, if my counter is 1, this exponent is 0, my first term is just going to be 10. Okay, so that's fine. What's going to be my second term? Well, I'm going to take 10 and I'm going to multiply it by the common ratio, which is 5 over 4, and I'm going to keep doing this. Okay, each time I multiply by the common ratio, that exponent increases by 1, and we're doing this 6 times. So that means the very last term is going to have an exponent of 5. And I want to know what happens if I take all 6 of these terms and I add them up. Well, I mean, you could brute force this. You get out your calculator, you plug in all 6 of these terms, you add them all up, and you would get here 461,160 divided by 4,096, which is going to be, approximately 112.587. And that's fine. I mean, it didn't take too long to get out your calculator and do this. But then the bigger question is, what if I didn't want to do just 6 terms? Okay, what if I wanted to do the sum of the first 50 terms, doing 10 times 5 over 4 to the power of I minus 1? What if I wanted to know that summation? Okay, and this is where we really feel the need to develop on that pattern behavior that we saw in the earlier example. Really, what we want to know is what happens in general for a geometric series. Okay, how can we know what the sum is going to be based on the values looking at A, looking at R, and here looking at N? Okay, those are going to be the 3 things that come into play when we determine the sum of our geometric series. So the question we want to answer: is there a faster way to add up the terms in a finite geometric series? So if we are looking at the sum starting from 1 and going to n, and we're adding up a times r to the I minus 1, we know that here, if I look at these terms, the first one is a, and then we have ar squared, and so on. I keep adding these up. Let's actually put the last 2 terms in this time. So I know that the very last term would be a times r to the power of n minus 1, and the second last term would be a times r to the power of n minus 2. So our question is, what is this summation going to be equal to? Okay, and we're going to develop here a very nice formula. This is essentially a proof, okay, and the notation gets a little bit messy. There's quite a bit going on, but I'll try to go through it slowly. And so here, the first thing that we start off by doing is a little bit of a trick, and we're only going to sort of use it for this proof. We're going to take this value, take the entire summation, and we're going to multiply it by r. Okay, why we do this, it's not clear, but you'll notice why in a moment. Okay, I'm going to take everything and I'm going to multiply it by r. So fine. That means that every term here in our sum is going to be multiplied by r. So that means that a is now going to be a multiplied by r. We have a times r will become a times r squared, and really just every term is going to have the exponent of r increased by 1. That means that this second last term is going to become a times r to the n minus 1. And this very last term is going to become a times r to the power of n. Okay, so we took our sum. We didn't know what it was, but that's what we're trying to solve for. And we multiplied it by r. So why did we do this? Well, we did this because now we can do this second trick. I'm going to take this term here and this term here, and I'm going to look at the difference between the two of them. I'm going to take the first one and I'm going to subtract from it the second one. So here, let's write out what that gives us. If I have the sum starting at 1 and going to n of ar to the I minus 1, and I'm going to subtract from that r times the exact same summation, something very useful is going to happen here. Okay, so if I'm doing this one minus this one, then you'll notice a lot of these terms are going to actually directly cancel each other out. I have AR minus AR, so they're going to cancel. I have AR squared minus AR squared, they're also going to cancel. These two will cancel. This AR to the 4 would cancel with the term that's right there, except obviously we didn't write it in, but it's nonetheless going to cancel. This term here would have canceled with the previous term there, which again we didn't write in, but it's definitely going to cancel. These two terms will cancel with each other. And looking at everything else, there are going to be two terms that actually don't cancel. We have the very first term and the very last term don't cancel with each other, which means that this difference right here is actually going to be equal to a, our first term, minus ar to the n, which is our last term. So that's fine, except our goal here was to find a nice formula for this summation. So what we're going to do is we're going to treat that summation essentially as an unknown variable, and we're going to solve for that unknown variable, which means I have it on here the left. I'm going to now start by factoring out that unknown variable. So I have these two terms. I could factor a times r to the I minus 1. What does that leave me with? Well, that leaves me here with 1 from the first term. And if I factor it from the second term, I'm left only with this negative r term. So I end up with this on my left-hand side. I have my summation multiplied by 1 minus r. On the right-hand side, let's factor out an a. So I have a times 1 minus r to the power of n. And now we are actually very close to getting to our formula. The very last thing that we need to do here is just divide both sides by 1 minus r. And what we end up getting is going to be that our summation for a geometric series, the sum of a times r to the I minus 1, is equal to a times 1 minus r to the n divided by 1 minus r. And that's exactly the formula that we were looking for. We could now use that anytime we want to know the sum of a geometric series. And again, all we need to know is what is a, what is r, and what is n. So our conclusion then is for a finite geometric series, as long as a is not 0, again we have that restriction on a. We also have this sort of new restriction that r is not 1, right? Why is r not allowed to be equal to 1? Well, looking at this formula, we can notice that we had to divide at one point by 1 minus r. So we also cannot have that r is equal to 1. Our common ratio cannot be 1. Fine, but as long as we have those two conditions, this is going to be the formula that we can use to find the sum for our geometric series. And that means that going back to our summation, when we were doing the sum of 50 terms, I was adding up 10 times 5 over 4 to the I minus 1. Now I can just use this formula. I know that a was 10, and I know that r is 5 over 4, and n is 50. So I have a is 10, I plug that in, times 1 minus r, which is 5 over 4 to the power of n, which is 50, divided by 1 minus 5 over 4. And now all I have to do is just plug this little formula into my calculator, and I end up with 2,802,556.93. Okay, so it's much, much faster. This formula allows you to find the sum for a geometric series with just some very minor computations. Okay, so I'll do a couple more examples where things get a little bit more complicated, and then we're going to move on to connecting this to annuities. So here we're looking at two examples of geometric series, and we're going to be using our formula that the sum of our geometric series is going to be a times 1 minus r to the n divided by 1 minus r. So looking at the first example, we can see that we're adding up here 12 terms, so that means n is 12. We have the very first term in our series is 30. Okay, so a is going to be 30, and our common ratio is 3 divided by 2. So that means that this geometric series will be 30 multiplied by 1 minus 3 over 2 to the power of n, which is 12, divided by 1 minus 3 over 2. And if you plug this into a calculator, you will get 7,724.78. So that would be the sum here of our geometric series, and I say that it's going to be sort of approximately this value because I did end up having to round it off. Okay, so now let's do here the same thing in the second one. In this case, we're adding up 24 terms, so n is going to be 24. And we have A is 1,000, and we have our common ratio is 1.07. Okay, so in this case, fine. We plug everything in again. We have 1,000 is A, multiplied by 1 minus 1.07 to the power of n, which is 24. And I divide all of that by 1 minus 1.07. Plug that in, and we end up with 58,176.67. Okay, so again, it does not take very long to add up these geometric series as long as you know the pattern, as long as you know the way that they're going to work out, and that pattern is given right here by that summation formula. Okay, so now in the next portion, what we're going to look at is the connection between a geometric series, which we're now comfortable working with, and an annuity. And we start off by defining what an annuity is.